here we go. Okay, so there's a graph. I'm trying to get mine to pull up. Turn your page over from the, if you're on the big table, there's a graph with a big like loop-loop. A little roller coaster looking thing. Okay, before I tell you anything about this, we are going to practice what you have to do all the time on the ACT science portion of graph interpretation. Right? If you haven't taken the ACT or you've never realized this, that's all the science section is about. It's just interpreting graphs. Knowing content can help, but it's not needed. It's just interpreting graphs.
Reading section.
Yeah, it's like reading graphs, reading data scientifically. Okay, so what I want you to do, don't say it out loud, just think in your head for a second and see if you can tell me what do you think this graph is representing. So take a minute to yourself. Okay, turn to your table buddy and tell them what you think. What is this graph represent? Go!
Oh yeah.
The lowest energy.
And then as it goes further, energy goes back up to 0. And then once it gets farther,
Okay, let's hear some ideas. Thank you for participating. Everyone have a smiley face, by the way. I heard good thoughts. Some of them, I'll be honest, are wrong. But I'd rather have, this sounds bad, but you know what I mean here. I'd rather have you have wrong thoughts than no thoughts. Okay? Because it's just what will help the brain get to the right place versus you just waiting for it to be handed to you, right? That's not how learning happens. The brain has to do some thinking to get there. So, okay, anyone willing to share? What do we think this graph is telling us? Now you're all nervous because I told you 7 years long. Yeah, go ahead, Zach.
I think it's the energy two atoms have as they get closer and further apart from each other.
So what logic did you use to come to that conclusion?
Because we have the two axes, and it says potential energy and the distance. So I was just thinking like the further they get apart from each other, the more the energy is closer to 0.
Perfect, and he's totally on the right track. And what he did is the way you should start any graph interpretation is starting with the axes. Right? What did the axis tell me? So this is measuring potential energy. This one is measuring internuclear distance. So internuclear distance is literally the distance between two nuclei, two different atoms. So what we get here is we get this minimum energy. Now keep in mind with energy here, we're going below 0. Right? Energy below 0 is because it's being stored within it. Right? The more energy stored inside, the more stable it is. Yeah, Max.
Well, if there's energy stored inside, wouldn't it be a higher potential energy?
Great question. So yeah, that's kind of the weird thing with energy is, do you guys remember, we've talked a little bit about it, but what does negative energy mean?
It's giving
It releases it?
Yeah, so when we talk about reactions, negative energy often refers to the direction. Now in this case, potential energy isn't moving energy, it's just there, right? And so the reason why it's represented as negative energy is that you would have to, let's say, put a value on that, 200, okay? You would have to put in 200 joules of energy to break that bond. but that's why it's represented as a negative value versus a positive potential energy for a bond would mean you would have to like, you're like forcing it to actually happen. Does that kind of make sense, the difference a little bit?
So I guess I was just like wording it wrong in my mind.
Yeah.
'Cause, yeah, I get it now.
No, and it's, negative energy is a weird thing. And I mean, we'll talk about it tons because energy is such a big part of chemistry. But I'll think if I can think of a better way of putting it. So this right here represents when two atoms, and this by the way is a graph for hydrogen. So when hydrogen bonds with itself, so H2. Okay, so here's hydrogen's nucleus. When it bonds with another hydrogen, I guess we'll put it inside a nucleus. Okay, its orbitals, right, overlap at this perfect distance. The internuclear, did I start my camera? Is it recording?
Yeah,
Yeah?
I think so.
Okay, thanks.
Yeah.
It tells us the length of these two nuclei from each other, or in a sense, the bond length between them. Now let's talk about why the graph changes in both directions. Okay, if I decrease my bond length, so I'm going this way, why does energy spike like crazy?
Because they're close together.
Why don't they want to be close together, Evan?
Because positive or two things with the same charge.
Yeah. Right? If these two things start getting too close, and Taylor, I think you were saying the same thing, the nuclei push each other away. Right? So energy goes crazy in the sense of it's not going to do that unless you're forcing it to happen. Let's go the other direction. So this direction would be like trying to overlap, right? Now that nuclei are going to be way too close, they don't like it. What's happening as I go this way? Why does it plateau out? Yeah,
Maybe
Carly?
they like repel each other and so they get more distance.
Yeah, pretty much at this point, they're not even bonded anymore, right? If you start pulling the atoms so far apart, you don't have a bond length because you don't even have a bond. And that's why it plateaus out and then it goes to zero eventually. So this right here is the perfect distance at which the molecule can exist. Okay? All right, with your table buddy, come up with a line to represent oxygen bonded to itself. So if this is the graph for hydrogen, H2, can you come up with an idea, so draw it, of what it would look like for oxygen? Would it be the same? Would it be different? Talk to your table buddy, come up with a line. Go.
It's gonna be five guests like this. And then we're done with I know it has a smaller unit of radius.
Oh, the new place. Yeah, okay, sorry.
No, you're perfect.
Okay, anyone
I can't.
brave enough to come draw their line on the board? Bryce will come draw his line.
Yeah.
Anyone? You don't have to be right. I'll give you a smiley face, but just be brave. Okay, come on up, Taylor. Evan, you can come draw yours too and see, we'll compare them. Evan, you come too. You can see if they're the same or if there's differences in our thoughts. Oh, so draw on the graph, so we can compare them side by side. Yeah, you're good.
I don't wanna miss this little, like,
You're fine.
I'm just gonna start there.
Okay, just to understand, Evan, are you drawing the exact same line?
Yeah.
Yes, okay, just wanted to make sure. Okay, anyone else have something different than these two they want to add? Different thought? Isaac can draw. It's blue.
It's a bit of a light green right there.
Yeah, we'll darken that line a little bit. Do you even see it from back there?
Still starts in the same spot, but it takes a little bit more. Get up, that's the same.
Okay. All right, let's talk about it. How's my face you three for being great, even if you're wrong? Okay, so once again,
No! Dude, it's over. You lost.
okay, go into our axes. So first off, our x-axis is the bond length. So how far over this dip goes, in a sense, is telling you the length of the bond. So whether you meant to or not, Isaac and Taylor are claiming that the bond length is going to be longer. Were you both hoping to make that claim?
Yes.
Yes? Okay. That is true. So have a smiley face if you major shifted to the right. Why is O2 going to have a bigger bond length than H2? Yeah, Max?
Probably because it has more shells, so
Oh, no, I was right.
it bonds farther away.
Yeah, because we got now, what, 2 rings on oxygen? So by default, that's just going to make, right, the distance between those two have to be farther apart. So, very good. Okay, now, yeah, Kimberly.
I was justifying that with like, it has a bigger nucleus, more protons, so that they'd be able to repel each other better, so they have to be a little further away. Does that play into it? Or is it mostly because there's another?
I'd say it's part of it, because that would be in the sense that we were comparing like the same row.
Gotcha.
So like helium versus hydrogen. Helium doesn't technically bond with itself, but let's say for example's sake it does. I would propose that helium would be a little bit shifted over because of that reason. So yeah, I think it's still valid.
Okay.
Yeah, Max.
Isn't that like kind of the same thing? With like the more protons you have, the farther out the shell that you need?
Generally, yes. Yeah, because the more protons you have, the more rings you're going to have, so the farther it's going to be. The difference would be like, once again, if you're comparing the same row, because the same row, right, would have the same number of rings, but, right, so like comparing like nitrogen and oxygen, right, type thing. So, but, okay, up and down, what does the up and down tell me? The energy of it, right? So it looks like all of you kept it at about the same height. Did we mean to do that? The two who wrote it up here?
That was the plan.
Yeah? Just making sure I'm remembering that. Okay, so you get a second smiley face if your distance is the same distance as this. So one smiley face for shifting it over, one smiley face for the down. So up to 2, but you could just get 1. Now, something we'll learn more about that could affect the scoop of the line. Let me draw a third one on here for you. What color have we used? We have black. This, relatively speaking, according to my drawing, is the line for nitrogen bonded to itself. Oh wait, let me fix that. Well, okay, I'm gonna fix theirs. Okay, so this blue one's gonna be our correct oxygen, just to erase so many lines. So oxygen, be like that. So first off, why would nitrogen and oxygen be similar in distance? In bond length, I guess? Yes.
It has like the same amount of protons and shells.
Yeah, like they're pretty much the same size, right? So that's not going to change a lot. But we get a pretty good sized decrease or increase in stored energy. Any thoughts of why? Yeah, Taylor?
Because nitrogen has a half subshell.
Ooh, it's kind of related to that. And once again, this is kind of a stretch. Well, in the sense that we haven't learned this yet this year. For those that have taken chemistry before, maybe in other classes you have, it kind of deals with that, but it's about how many times it's bonding. When hydrogen bonds with itself, it forms what's called a single bond. When oxygen bonds with itself, it forms a double bond. When nitrogen bonds with itself, it forms a triple bond. Triple bonds have more stored energy than a double bond, because in a sense you're sharing more electrons. So the more you share, the more overlap you get. Yeah, Zach.
And why doesn't hydrogen have more energy than or oxygen have more energy than hydrogen?
Good question. Thoughts on why? Why they're about the same?
I don't know.
It's kind of that it gets canceled out by the distance, right? So yes, it does have more electrons being shared, but since it's so much bigger, it kind of breaks even. So good observation though, because generally speaking, you would assume that a double bond is going to have more energy than a single bond would, normally speaking. So, yeah, Evan.
So like fluorine, since it's a single bond, it would just be higher up. Like there would be less potential energy.
Yeah, good observation. So fluorine would be, let's see, probably similar in size, right? But it would probably be even less than the other one because it's just a single bond. Yeah,
Okay.
no, great observation. Any other questions on these internuclear distance graphs? I've never seen them. I turned it into a free response type question. I've never seen them actually as free response, but I have seen them often as multiple choice, of where they give you one and then you have to answer questions about it. That's what your quiz 2.2 tonight will have you help practice. So, yeah, Kimberly.
Can you explain one more time why the double bond is still the same, like,
As the hydrogen, it's just because since hydrogen is so small, right, like those two nuclei, because it's only one ring, can get really close to each other. And because it's so close, it's fairly strong. You can also think of the bigger this is, the stronger the bond is, right? So the strength of the bond is fairly similar because they're so close.
Gotcha.
So yeah, it's mostly just because of that. But if we were to compare, like, hypothetically, like carbon. So carbon does double bond at times. C2 isn't a theme, but we'll just pretend. Okay? So this bond, in comparison to that bond, right, would probably be, like, they'd be, like, pretty similar in energy. Or in a sense, like, a single bond would be less because of the size. So it's kind of like you just have to compare both of them in terms of, like, the size of it as well as how many bonds are forming. So, yeah, good clarification. Yeah, Carly?
Sorry, mine is just a clarification too.
Yeah.
So the distance depends on how many like rings are electrons.
Yes. As well as how many times it shares. Because the more, it does go into the fact that a double bond is going to be shorter than a single bond. But only of like that exact same element. So like this is going to be shorter than this, which would be shorter than that.
Okay.
It gets a little weird when you start comparing different elements because they're different sizes in general, but yeah. Any other clarification questions on these graphs? Okay, let's continue this. So that kind of talks about the bonding and how they overlap with each other. Let's talk about ionic substances. Oh, sorry, some words to fill in. This is to just kind of help you have some reference because your book doesn't really talk about these graphs very much, but it is a big part of the AP curriculum. So the internuclear distance is the point at which the potential energy minimum occurs, and it's defined as the bond length. Okay? Keep in mind that this is more correctly known as the equilibrium bond length because bonds are not actually rigid. Atoms, in a sense, are constantly vibrating. And so technically the length of that bond is constantly changing. But the point that's measured on the graph is the equilibrium between them, meaning it's the average of what's happening through the vibrations. Okay? And then in general, the stronger the bond, the shorter the bond length will be. And then these graphs can also help us understand why certain things don't exist as bonds, is because if the attractive forces between them can't overcome the disruptive forces of pushing away, like this pushing pull idea, right, then you don't get a molecule. Like they're just not going to bond with each other. Kind of how you can measure, in a sense, why two things won't bond is because the pushing outweighs what's holding it together. So it just falls apart on its own. Okay, ionic substances. Okay, so let's jump in our magic school bus and fly into a grain of salt. This is what it would look like. Okay, we see positive, negative, positive, negative, positive, negatives. Okay? We call these structures a crystal lattice. Okay, ionic substances are a crystal lattice. They're all crystal-like. Okay? That's why to break them apart, we call the lattice energy. So energy is the force that it takes to pull apart an ionic substance. Okay? For sodium fluoride, it has a lattice energy of 930 kilojoules per mole, meaning I have to put in that much energy to, in a sense, break the bond. You can kind of relate to it's like the bond energy. We just call it the lattice energy because we don't really actually know who's bonded with who originally in a crystal lattice, right? It's just positives with negatives in three-dimensional space. Okay? Magnesium fluoride has a lattice energy of 2,978. What I want you to answer for me, so think in your head first and then we'll share with our table buddy, is why is this one higher than that one? So why does it take more energy to break magnesium fluoride than it does sodium fluoride? Take a second and think to yourself. Okay, turn to your table buddy and share with them what you think. Go.
I would say he says magnesium. Watch it be like
They're both well, yeah, they're both stable. I think this is like
Thanks. Okay, anyone willing to share their thoughts? Why do we have this big difference of lattice energy, Isaac?
The sodium fluoride only has one bond between them, but magnesium difluoride has two bonds.
True, I'm going to just change your wording a little bit, but you are on the right track. Because it's not really like, because keep in mind we're not sharing electrons here, right? But it's the transfer of them, so it's really their charge, right? This one has a +1 and a -1, which I think is what you were saying, while magnesium is +2 and a -1. A +2 magnet is going to hold on tighter than a +1 magnet, which means the tighter the hold, the harder to break, meaning more energy required. Good. If you had something along those lines, give yourself a smiley face. Isaac, you can have 2 for sharing. Okay, so what we get here is... Hi.
Hi, Jamie. Can we interrupt your class for just a second?
Sure.
I have a few visitors that would like to join us as well. Come on in, guys. Hi. This is Superintendent Jarman,
It's great to be with you.
members of the Cabinet and the Alpine Foundation. Okay.
Who would like to do Tyler, we're gonna let Tyler.
So my name's Tyler Vigio. I work with the Alpine School District Foundation. So basically, guys, my job is I go out to the community and I say, ask them to help and support things that they care about in our schools. And one of the things they really care about and always want to make sure that we do and do well is honor some of the best teachers in the Alpine School District. Any guesses? Okay, all right. So I'm just really happy to do that. Normally, we would do this a little differently, but of course in 2020 we don't do anything normally. Everything is new and different and unique. So we decided to come in today. So Jamie knows that she got this honor. It was actually last school year. She was Teacher of the Year at this school. She was and Teacher of the Year for what we call the cluster, so all the schools that feed into Skyridge. And so with that honor, we want to present some things to her today. So our superintendent's here, so I'll turn some time over to him to say a few words.
Okay. So the first thing we want to present you with is this crystal. And I'm going to let you hold the crystal up because then it's your fingerprints. No, I want you to grab the crystal, yeah. It's heavy.
Over your head now, over your head now.
I feel like I'm in a Despicable Me movie or something, and the minions just went, oh.
They're good at responding.
All right. This is something that we have over 4,000 teachers in our district, okay? She's being recognized as one of the top 10 this year. So that's pretty awesome. More important than the crystal is this piece of paper, which is a check for some dollars. That I believe it's $500. Is that correct? $500 that the foundation, through the donations of the companies, have made available, and she gets to spend this on her. Aren't we happy that she gets to have that? So congratulations. I know we're not supposed to hug and do the handshakes, but I'll give you an elbow. How's that?
There you go.
What a wonderful experience. Hopefully you recognize as students that you're having with this teacher. So, back out of the way. Thank you.
Just to add a little more detail there too. So again, as we go out to the community, some of them, like Alpine Credit Union, EMI Health, and others give us cash, right? So we're able to give some cash. But then others give us some cool stuff. So we want to present some stuff to her today too. So for example, there's this cool little bag. It can be maybe an overnight bag. You might take that bag and load it up, and then there's a certificate for a one-night stay over here at Home Suites. So maybe you, I mean your husband's in the room, so I'm not going to make payments for you. But you know, there's some great, like a doTERRA diffuser, maybe some books, things you can go and have a nice relaxing weekend. Maybe you want to splurge and use your cash down at the outlets while you're there. I don't know, that's up to you, right? But then I hope, whether you're then or other times, I hope you'll really enjoy the Sierra West pearls that Sierra West has provided too. So those are some of the examples of things we've got. There's some others in there that you'll see. But again, we're so grateful for our community stepping in. We're so grateful for you. So thank you and congratulations. So I can give them their homework, and they're thinking, stay. Thank you, Jamie. So, can we get one picture? Yeah, we get a picture.
Where do you want this?
However, well, we're at the end of the so wherever you speak.
You probably ought to turn on the projector and do that, if that's okay. Okay, so is this chemistry or AP chemistry or what? AP chemistry? Awesome.
Nice.
Good job, you guys.
Okay, can we fit back here? Is that good back?
And so are you streaming this? So hi to everybody who's...
They're clapping.
Okay, let's get her husband. Yeah. Get Juwan, get next to your wife.
That might be a good idea.
Yeah.
Scoot over this way just a little bit. A little bit more. Scoot.
I know. Okay, then this one.
Biggest smiles ever.
I know, I can tell you're smiling.
I know.
Yay!
You get what you need? Nice, awesome.
Alright.
Way to go! And I thought I was gonna get out of getting embarrassed though.
And by the way, not only for her teaching, but as her coaching assignments as well in track and cross country. Thank you.
Thank you.
She's the best, right?
Okay, I'm gonna have to edit all that out. Make him part of that.
In honor of this momentous occasion, we should all get 100% on the tests.
You know, I don't think that's why I got this award. I think it's because I don't give kids hundreds. Thank you. Yeah, I really thought, because, so I got it last year, but we were on shutdown, and they're like, yeah, normally you'd come into your classroom, and so I was like, oh darn, I missed that. And then they showed up today. I thought it was okay, we gotta get, we gotta figure out what to do, because we're behind, and we got 4 minutes left, but that's okay.
No homework.
Well, we gotta simplify your homework. Don't tell B6. You only need to do quiz 2.2. Come in again. No, it's bad because then we're gonna get behind schedule. So we gotta. Next time we might have to go double time at the beginning to get caught up.
We can take the test a day later.
No. You don't understand. You want to see my planner, Taylor? You don't understand. I have everything mapped out till May. So like this test gets pushed back, and then it's gonna push something else. Like it's a domino effect in AP Chem. So we'll figure it out though. Somehow.
Well, the online students know too.
This thing is heavy. I almost broke it.
It's gorgeous.
Except I'm like making it so dirty with my hands.
You should get like Windex.
Yeah, that would work out.
That's actually so light. Where are you gonna put it?
I don't know.
On your desk. Everyone should see.
You should like hang it from the ceiling
Like if someone came through, we could use this as a weapon. This is solid. I don't know. I guess we put it in the window and then we get like rainbow shades ionically.
Yeah.
Oh, that's pretty cool.
Is that like cool?
I can see a rainbow right here.
I can see
Colors.
rainbow.
Now I feel like I want to get wet. And that's probably pretty safe not to get knocked over, right? Unless earthquakes happen.
Right.
If earthquakes happen, they're bigger problems. Man, they gave me a puzzle.
You just take a whole day and do that.
Honestly, if any kids come and harass me, you can just be like,
Look at my crystal. Look at it.
Get out my classroom.
So does that mean I'm done? I don't have to try anymore? Is this what that means?
Yeah. If it's your passion, you've already got some.
So, okay, well, so mostly, I guess you should get your lab done because you don't have much other homework to do tonight, right? So, I guess we can stop this now. Sorry, at-home students.